We're still in section 3.1, still graphing systems of equations to solve. We like to take our equations and put them into what form in order to graph them? Slope-intercept form. There's lots of different ways that we could graph them, but we are going to choose the slope-intercept form. So in the first equation, to put it in that form, I'm going to start by subtracting x. When we subtract x, we're left with negative x plus 3. Y equals negative x plus 3. The y-intercept we know is at 3, so put a dot at 3. Our slope is a number that's in front of x. In our case, it's negative 1 over 1. So I'll go down 1 and right 1, down 1 and right 1. And remember we talked on Friday that we like to extend our slope as far as we can. We're trying to find an exact point where these graphs intersect. So extend that as far up and down as you can. And then you can take your straight edge and draw in your line through those points. For the second equation, we need to put that in slope-intercept form. We're solving for y, so I don't want to divide by 2 just yet. What would you do instead? Good, I agree. I would subtract 6. So we have 2x minus 6 equals negative 2y. We're solving for y, so we need to undo multiplication with division. Divide everything by negative 2. So we're left with negative x plus 3 equals y, or y equals negative x plus 3. What do you notice about those two equations? Exactly the same. The signs are the same, the variables are in the same place, the same constant, everything is exactly the same. So when I graph this second equation, it's going to be right on top of the other one that is already there. So think about how we're going to write our solutions. If it's the exact same equation, we graph the lines on the exact same place, where do these lines intersect? Everywhere, don't they? They touch, they intersect everywhere. So we would tell our solution as, or write our solution as, not all real numbers. We would say infinite solutions. We use all real numbers to describe an equation that we're solving if we put any number we wanted in. This says we have infinite solutions. We really can't put any number in. So instead we're talking about the number of solutions. We have infinite. On Friday, we talked about classifying numbers. Flip back to the front side of your page if you forgot these classifications. Consistent. We said that means that there's at least one solution. Do we have at least one solution? Yes. So it is consistent. Is it inconsistent? No solutions. No. Is it independent? Exactly one solution? Is it dependent? Infinite solutions?
Yes.
Yes. So we have consistent and dependent. Let's do the last example, example 8 in your handout. The first equation you'll see is already in slope-intercept form. So let's plot that. We have a y-intercept of 2 and a slope of 3. For the second equation, I would add 6x. So we have 2y equals 6x plus 10. Divide everything by 2. Do you notice anything about these two equations before you graph the second? Same slope. What does that tell us?
Parallel.
It should definitely be parallel. Two parallel lines never intersect. Our solutions are where the lines intersect. So what would we say our solution is here if they never intersect? No solution. You can either write out the words no solution or use the symbol for no solution. Let's classify this. Is this system consistent? At least one solution? It's not. Is it inconsistent? No solutions.
Yes.
Yes. Is it independent? Exactly one solution? It is not. Is it dependent? Infinite solutions? It is not. Today, you have 40 minutes. I want you to practice some of these problems. I have a worksheet, I have a graph paper provided for you. I want you to make sure you're using a ruler, a straight edge to draw in the lines. I want these to be precise. If you're off just a little bit in your graph, that makes a big difference as to where your lines intersect. That ordered pair will change. So please do make sure you're using a straight edge.